Good afternoon, everyone, and welcome to today's webinar, Groundbreaking Developments in Liquid Filtration, brought to us by the Donaldson Company and lead development engineer, Coulter Marks. My name is Dolores Alonzo, the Senior Director of Membership at FPSA. Before I pass this over to Coulter, just a few housekeeping items for today's webinar. Many of you may be listening in using your computer system by default, but if you'd prefer to join in over the phone, just select the telephone in the audio pane, I believe, to your right, and the dial-in information will be displayed. All attendees are muted by default, but you will have the opportunity to submit text questions to Coulter today by typing them into the questions pane of the control panel, and you can send in your questions at any time during the presentation, and we'll address them at the end. The presentation also is being recorded should you want to share it with colleagues who could not attend today. So I am going to pass this over to Coulter now. It will take a few seconds for his screen to come up. And thank you again for your participation. Hi, Coulter, are you with us?
I'm here. Thanks, Dolores.
Terrific.
You let me know when you can see it, and we should be off to a good start.
Okay, I think we're good to go. Thank you, Coulter.
Okay, thanks. Well, hello, everyone. Good afternoon, and welcome to my webinar, Groundbreaking Developments in Liquid Filtration. My name is Coulter Marks, and I'm an engineer at the Donaldson Company. We're approximately a $2.5 billion global manufacturer that produces filtration solutions for many industries, from the air and lube filters on trucks, buses, and construction equipment, to things like airplanes, cell phones, hard disk drives, and large dust collection systems used in manufacturing. My particular business unit is called Process Filtration, and we serve mainly the food and beverage industries with filters for compressed air, steam, liquids, usually with the design intent to remove contaminants like bacteria and other pathogenic or spoilage microbes in order to ensure product safety and integrity and protect both producers and consumers of those higher risk products. I've been in this group for nearly 4 years now. I've been with Donaldson for my entire career after college, starting out as a lab technician working with diesel fuel, filter water separator technologies before joining this group and being able to participate in this new exciting solution development. I'm going to talk to you about a few topics specifically related to sterile filtration. First of all, of course, a bit about why sterile filtration is needed, where it's used, and what's special about it compared with other technologies. Next, I'll describe what I would call the big three problems in the industry today, starting with the fact that this product and technology itself has been essentially ignored and untouched for a long time, despite the fact that it's a very critical step in certain production processes. I think that part of the problem is related to the typical hesitation of producers to try the new things. You know, nobody wants to buy serial number one of anything, for example, because you feel like there's nothing really in it for you except for undue risk. These types of polymer process filters used to be a specialty back when new medias like EPTFEs, polysulfones, polyether sulfones, etc. were developed, but as time went by, more and more people started copying the same thing, and it became more of a commodity item. Nonetheless, the food and beverage industry has continued to grow and innovate, and these filter technologies just haven't kept pace with the industry production demands. So we here at Donaldson have recognized the need for improvement in order to best serve our customers, hence the new product line LifeTech was born. These big three problems I mentioned really focus on the ability to produce product at a fast rate, and this is called throughput or flux. In this case, our product is a sterile fluid stream. As other equipment in the plants, like bottle fillers, mixers, conveyors, etc., have improved in speed and efficiency, we really wanted to make sure that we could create a filter that produced enough quantity of sterile fluid to meet the capacity of these newer, faster machines. One of the difficulties here is to accomplish this while staying within a well-established physical design boundary of the product. All of these filters in the market are about the same shape and size and come in lengths of 10, 20, 30, and 40 inch with a little under a 3-inch diameter. So our solution here needed to be internal to this envelope, and I'll describe how this was done in more detail later. The next big problem relates to the integrity and life cycle of the elements. A sterile filter's life is dictated by the amount of time it is able to continually produce a sterile filtrate. So processes like steam sterilization and hot water sanitation are quite hard on the assemblies, and eventually the degradation and stress of these materials caused by the harsh processes will cause the filter to fail integrity, and therefore it's no longer possible to use that filter to sterilize a fluid stream. The longer the filter remains intact, the better protected the product is, and the longer that filter is able to remain useful in the process. The last problem is related to replacement and total cost of ownership. This is somewhat of a summary of the big two design improvements that were made here, but it all boils down and relates back to dollars in the end. In the case of throughput, you're able to produce more product with less, which is the cost savings. In the case of the integrity and life cycle, the longer the filter is in use, the longer the time and the greater the production, the cost of that filter can be spread over, which means a lower cost of ownership. Lastly, I'll briefly cover the solutions used to achieve our improvements. My goal here with this presentation, first and foremost, is to make sure you understand the problems that exist today and how there's a solution to these problems, not necessarily exactly how we went about addressing those problems. But I'm confident here that we have something of a technical audience here that might benefit and enjoy learning a bit about these nuts and bolts of this technology as the current state of the art. So I'll briefly touch upon how our medias and improved pleat pack designs allow for a higher throughput. I'll show an improvement in the cage and support structure of the element that leads to a better integrity and longer useful life, and how a purpose-designed production process allows for a low quantity production runs to happen quickly and easily. So why do we need sterile filtration? Most people, besides myself and some of my colleagues, really don't care much about sterile filters. They really care about what that filter does for them. As I mentioned earlier, it's all about protecting the consumer and protecting the profitability and brand integrity of the producer. In other words, it's low cost and high effective quality control. On the right side of this slide, I've listed some of these products and industries that really rely on these filters to provide this protection. Food industries in particular rely on the technology to minimize infection and recall risk, especially in microbial sensitive segments of the industry like dairies. In beverages, more in particular the alcoholic ones, we're concerned with ensuring the reproducibility of the process. So beers and wines don't really have the possibility of being infected with pathogenic microorganisms, but there's definitely a risk of getting spoilage organisms in those products, and that'll make an otherwise very tasty, desirable product become something more fit for a floor drain. Dumping out products costs a lot of money. And last but certainly not least, the biologically active ingredients in products in the healthcare and biopharmaceutical markets. Not only are these often susceptible to infection, but their target users are that portion of the population that's most at risk of suffering the adverse effects of an infection. So it's the very young, the very sick, or the very old people. And they're the ones that are at the highest risk from having a serious illness caused by these infections. But in all these industries, we're trying to do basically the same thing, although in different orders of importance, depending on the application. So one of these is shelf life. We want to extend the window of sales opportunity for the perishable products, which both reduces the scrap rate for that product and also gives a better chance for being purchased. The product consistency. A given product is successful really due to its unique and desirable flavors and characteristics, so we must match that every single time during a production process. There's lots of opportunities for external variables and microbial contamination to alter product and change its consistency or flavors in a negative way. Next is the safety. Consumers must be protected from outbreaks of dangerous pathogens caused by microbe ingression at critical control points. There's lots of opportunities for these things to get in, especially in fluid transport streams, so we really need to have something to provide a safe measure of removing these things at these critical points. And lastly is economics. All these things really contribute to the overall profitability of producers of perishable food and beverage products, and they have an impact on the bottom line. Brand image is of incalculable significance, and it doesn't take more than a single real public recall to have a very impactful negative consequence on a business. The sterile processes are required anywhere that make ingredients of a high-risk food is introduced. In this example, we're making sterile water from an unfiltered source, such as a municipal supply, water well, or surface water source. In an attempt to make this a one-size-fits-all representation, I've included all of the filters between the source and the outlet, but I've omitted any example of the application just to keep it simple. So we can consider it to be anything we want, maybe a bottled water manufacturer, just to keep it simple. What we're doing is taking a water source and first pre-filtering it to remove the big stuff like sticks and stones and moss and sand and rust pieces. Next is an activated carbon filter to remove chlorines, chloramines, and other adsorptible materials that a traditional sieving filter can't remove. This would really be more typical of a city water supply and might be either unnecessary or simply not desired in a spring water factory, but it represents the need to remove these things nonetheless. The third in line is a membrane pre-filter, which is one of the most important parts of the system as it's responsible specifically for protecting the really expensive sterilizing final filter from early fouling. So even though a lot of people like to concentrate on the sterilizing filter because that's what's really doing the job at the end of the day, it's almost more important to look at the pre-filter because that's the part that's going to provide the most economic impact if you choose it wisely. So even though it's not rated to remove bacteria, it's really one of the most important parts. And lastly, the sterilizing membrane itself. After this filter, the water is visually clean, free of most chemicals, and presents no risk of contamination from pathogens such as your typical water organisms, the cryptosporidiums, Listeria, the list goes on and on of things. Bacteria, just like all living organisms, like to have an environment, that has the right temperature, that has water, and has some sort of a food source. So it's a water system in general is just necessarily a nice environment for them. You might also notice here that there's a red line plumbed into the installation. So this piece of equipment in that line is actually a steam filter, and the steam is used for the purpose of sterilizing the final membrane. This is because the membrane is operating every day to capture bacteria, or it builds up in concentration over time. Since the sterile filters are qualified by proving that they can produce, for example, a 7-log reduction in a microbe population density, we need to make sure that this quantity, which happens to be 10 million cells or bacteria per square centimeter of media before one is allowed through, is not exceeded. And it's just a good practice to implement this kill step periodically to the entire system that the filter is included in to keep it safe and sterile. The heat of the steam will denature the intracellular proteins in the microbes and basically render them unable to reproduce themselves, doing the typical multiply and divide process that microorganisms do, and it effectively kills them. It just makes them so they can't grow into a dangerous concentration. The reason the steam filter is there is because the steam filter will travel as fast as it can, and wherever there are cold surfaces existing that allow it to give up its heat, where it condenses, creates a partial vacuum, and pulls more steam behind it. So those steam systems typically operate at high temperatures. They're typically made out of a lot of carbon steel, and any dirt or rust particles at these high velocities in those systems have a possibility of impacting the sterile membrane and damaging it, rendering it a non-sterile filter and thus needing replacement. So that steam filter is an easy way to make sure that sterilizing steam is safe for the membranes. So why is the sterilizing filter rated at the 2 micrometer size? It basically has to do with the fact that 0.2 micron particles can be some of the most difficult to capture. So in the upper right corner here, you can see that we're really focused on the 0.2 to 20 micron sizes with these types of microfilters that I'm talking about today. And that's really for 2 reasons. Number one, that's the size of bacteria in general. And number 2, those sizes are some of the most difficult to capture. In other words, it would be the most penetrating particle size of a filter. So below that, in the lower right corner, we're trying to show a chart that shows the minimum retention efficiency and how that occurs somewhere in that 0.2 to 0.3 micrometer range. When you get smaller than that, it gets easier to capture particles, and when you get bigger than that, it also gets easier to capture. So the industry in general has kind of polluted this topic and made it difficult to understand, and it's typically counterintuitive that a very, very small particle could be easier to capture than a big one, but nonetheless, that's the case. And on the left side here, these are just some of the filtration mechanisms used to capture particles of different sizes. So you can see some of the smaller ones are captured by something called diffusion, where the particle isn't actually following exactly that fluid stream. It's got kind of its own random movements that might not be in the same direction of travel as the fluid stream itself, and that random motion makes it more likely that particle will contact a fiber of the filter and be captured. The second is interception, which works on a little bit bigger particle. Impaction, where the particle actually falls out of the fluid stream due to its inertia and its inability to remain in the path of that curving fluid stream through the tortuous path of the filter. And lastly is sieving, which is the most easy and obvious to understand, where the particle is actually too big to fit between the pore of a filter, or space between the fibers in this case, what the picture is depicting, and that actually gets trapped physically by the 2 fibers being too close together. So the first problem, as I discussed earlier, it's the throughput. As mentioned, the goal here is to have more product sterilized per cartridge, which means a lower cost both in terms of the original installation size as well as the ongoing element replacement costs. A smaller original install is a lower capital expense, and fewer elements to replace are a reduction in operating and consumable expenses. If the element lasts longer, which our design will show, replacement will occur less frequently. Less labor, fewer parts, and not as often. These are all three big cost savers. Lastly, the pressure drop through a cartridge has a direct relation to costs associated with pumping the product. This is because filters are necessarily a restriction in the system, and pumping through these restrictions uses more energy. That's why there's always a focus to reduce pressure drop when you look at filtration literature. We took the approach here of trying to design a filter by focusing on how much empty space we could get into that media, rather than focusing on how we could create the pores or holes inside of it. The reason, of course, is that a fluid can only flow where there isn't material to block it. So if you crunch the numbers, you'll find out that the units of pressure multiplied by flow rate have the same units as power, which is how the energy and the electricity is measured, for example, for pumps. So since no one wants to reduce flow rate, which would be reducing production rate, we really need to focus on the pressure side of that little equation needed to move that product. Taking restriction out of the filter yields an energy savings on the part of the pumps that are doing the work. So the costs are not easily associated necessarily with the filter, since you see them at a meter, but they are indeed related directly. So the second problem is integrity. How long you want to remain this sterile integrity for as long as you possibly can, and this determines the life cycle of the element. You'll notice that manufacturers of sterile filters always state the acceptable quantity of sterilization cycles in their literature that element is advertised to be capable of withstanding. The reason they do that is a proper pre-filter, that sterile membrane won't fail due to fouling or clogging up. It'll all get captured. The stuff that plugs up the system will be caught in the pre-filter, which is a cheaper piece. It'll fail integrity because that's the failure mode expected due to the design of the system. It'll fail after a sterilization cycle, not because it got too clogged up. So we want to keep it integral for as long of a time as possible so that we can replace it as least often as possible. Sterilizing filters are actually tested to remove real bacteria using an ASTM test that qualifies them as a sterile filter, but in real life we can't use this test to validate performance on the production floor. It's just unrealistic and it causes a risk of contamination. So we came up with other more user-friendly non-destructive tests like bubble point, diffusion, water intrusion, depending on the media, easier non-destructive technical tests that can be correlated to the results of an actual bacterial test. A bubble point test is really similar in principle to, for example, how kids blow bubbles with a bubble wand. So you dip the wand and the ring at the end of that wand represents a pore or a hole in the filter. You dip it in the bubble solution to wet it out, and then you must blow with a certain strength or pressure of air before that film in the bubble wand will leave the wand and allow a bubble to escape. So in a filter, you can imagine the pores being a whole bunch of little tiny bubble wands that we wet out with a liquid, usually water or a water isopropyl alcohol mixture, and apply a pressure usually much higher than what you could blow into a bubble wand, perhaps 10, 20, 30, 40, 50 psi, and try to watch for any bulk flow of air through that element, which would signify that there's a pore somewhere in that filter that's of a size that's not acceptable for the process. So here's a picture of a membrane media in the middle of the slide that kind of shows these pores. They're not perfectly circular looking on the surface, but they're holes nonetheless that the fluid must flow through while it captures the particles and microorganisms. The last problem is related to replacement costs. So there's literally hundreds or maybe even hundreds of thousands of combinations for these filters when you take into account the various options for things like end cap configurations, media materials, micron ratings, sealing elastomers, and the length of the element itself. Unfortunately, the manufacturer and the customer really want two different things here. A manufacturer wants high quantity production runs because it typically takes a lot of work in setup, dialing in the parameters, and getting the production running, dialed in and running smoothly with a low scrap rate for one particular design. Therefore, they try to really delay production of low quantities until enough demand is built up to do a quantity run. And that's not in particular to the filter industry. It's really most things in the world that get produced or manufactured, piece parts. You want to do more when you do a production run because it costs less to do more, if that makes sense. The customer, on the other hand, really wants no more pieces than what they need to use themselves, and they couldn't care less about the other 500 pieces the manufacturer wants in order to do a production run. So there's a constant pull between the production demand and demand for the consumer that makes it difficult for many filter users to get the parts they need when they need them most. And inevitably, they need them most when something unexpected and unplanned occurs. It's a real big problem. It can cause, plant shutdowns, which really need to be avoided at all costs. And it's really, unfortunately, those times at which something's most desired that it's hardest to get. So those are the three problems. Now on to the solutions. The product and installation you see here is the result of a global project involving the resources and participation of over 40 engineers here at Donaldson and material scientists working together with some of the biggest food and beverage industry leaders like Molson Coors, Coca-Cola, Nestle, and Danone to produce something game-changing, the LifeSec product. We couldn't have done this without the feedback and the hard work of our partners, and we're really truly grateful and confident that we have something here that is highly beneficial to those who choose to use the technology. So the first solution is an improved media pore structure and media pleat configuration itself. Filter pores are really, really small, sub-micron, but the media itself looks like a piece of paper if you take it out of a cartridge, and it's in fact very thick relative to the pore size. So you can think of it like a bunch of really long drinking straws going through a very thick wall. These long straws act like very small tubes and create a loss of pressure due to the fluid friction. So this is kind of similar. I use the analogy of a garden hose. Anybody that's used a garden hose, and if you buy one that's too long, you've got to put your thumb over the end of it or something to produce any sort of pressure to get a decent stream coming out of that. The water typically tends to just dribble out the end of a really long hose. And that's really quite analogous to how a pore structure in a media is. It acts like a really long, small diameter tube that causes a lot of restriction to the flow. So what we did here, and what I'm trying to show in the slide, is that we've got this tapered triangular structure where they're more open on the top and tighter on the bottom. Think of it more of like a funnel shape rather than a uniform tube. And what this does is it creates a much lower resistance to the flow, and it creates more of an area for contaminant to build up before the pore is completely blocked off. So the result's a higher capacity, which translates into a longer life, and a lower pumping loss, which translates into an energy savings. And the chart on the left here is showing basically capacity of one design versus another, and that typically would translate directly into longer life, especially in the case of things that are failing by clogging up. The second solution, and the most interesting one to me, is the cage strength. So this is more macroscopic and a lot easier to wrap your mind around since it's visible. These filters use extremely delicate precision structures to perform a really important job of removing entirely these bacteria in streams. Many of the materials have a very low modulus and are quite inelastic, so any deformation in that cage structure will translate to stresses in the media and can cause fracturing. So this is especially important in the cases of installation and removal. One of the most popular filter connection types is called a Code 7 or 226 with tabs is another popular way of describing it. It's basically two O-rings together with two tabs. The filter needs to be pushed into a socket and then twisted slightly to engage those tabs and lock it in place. And unless those O-rings are really well lubricated and the tolerances are on the looser side, a quite large torque must be applied to that to seat those tabs in the assembly. And over a long length of filter with a typical design of the past, these torques can cause a quite measurable amount of angular displacement and deflection in the assembly. And it's possible that that movement will translate to the media and the pleat pack and actually do damage to that cannot be undone. So what we did here is we designed a cage around a more triangular truss concept to replace the old square design, which you can find in many other designs of the past. So everyone knows that squares are basically a weak structural shape. Triangles are a rigid shape. That's why they use the shape on things like building roof and bridge structural members. It's because they're just naturally more rigid structures. We use that here. The second force is in the direction of bend, also called flexural resistance. This is the most important criteria under conditions of steam sterilization when the element is really weak due to the hot temperatures of sterilization. It's usually non-ideal process parameters during sterilization that cause an element to fail integrity. So the stronger we can make that cage when it's in this hot steam environment, the better protected the system is and the longer the filter can be used. The other solution is one-piece manufacture or low-quantity production runs. You can see pictures here of our new state-of-the-art facility that's located in Hahn, Germany, where our LifeSec elements are produced. This line was designed so that we could almost effortlessly produce an immediate demand for a low quantity of a particular design. So this will allow us to serve customers faster at the most critical times, like I mentioned before, that unplanned, really urgent need for something, eliminating the need to wait long lead times or pay a steep upcharge for a one-off production. So this is truly one of the greatest advancements, probably above and beyond the product design improvements themselves. And we can go here from product inquiry to delivery faster than I believe anyone in the business that I'm aware of, which keeps producers online and turns a large problem into merely a slight inconvenience at worst, I would say. So to summarize, I've shared some big advancements in a product that's been unchanged for a long time and communicated the benefits of these advancements in terms of safety, cost savings, and product and consumer protection. You can see here that all these things boil down to a lower cost of ownership. And lower cost of ownership can come in terms of several ways. It can come in terms of reducing scrap, keeping your product on the shelf longer, reducing the energy required to pump product, making sure that your brand is protected from those dangers of recall or product infection that can be just incalculably damaging, and just generally ensuring that the quality of the product is what it's intended to be, the producers is protected, the consumers are protected, and everyone at the end of the day is happy with the results. So that's really all the material that I wanted to share. If anyone's got any questions put in, I think I'm guessing that Dolores has collected those and might be able to share those at this time.
Yes, Coulter. I just sent you a few questions, but I have one here up on my screen, and it is, what is the filter efficiency at 0.2 micron?
So the filter efficiency at that size, you can state it in terms of an efficiency. It happens to be 99 point several nines in a row. It's kind of difficult to look at. And for that reason, that's why we rate these filters in a log reduction value. An LRV is typically what you see it stated as. And that basically means, how many of these cells of this size, 0.2 micrometer in this case, are allowed to be in the system, and the filter will effectively remove all of them. And what you're looking for in a specification here, if you're designing something that would require a sterile filter, is a LRV or log reduction value of 7. And what 7 means is it means that basically 10 to the 7th is the amount of bacteria that can be removed before anything can get downstream. So that'll be 10 million particles or bacteria, individual cells, per square centimeter of media. And that's what that means. So the efficiency is, like I said, you can state it in terms of efficiency, but it's really better expressed as an LRV, so you don't have so many numbers to look at and individually count.
Great, thank you, Coulter. And I'm not sure if you received some directly, Coulter?
Yeah, so I've got a couple here. Let me scroll over to them. So this one's pretty, I kind of covered this, but I'll go in a little more detail. It's just what applications are these sterilizing filters used in? So it's really those things, we focus a lot on food and beverage industry applications, but even more so, it's those within that industry that are the most sensitive, and not only the most sensitive, meaning things that are naturally supposed to have certain life forms in them, such as yogurt, for example. Yogurt is intended to be a live culture product. There's certain things in there that make it what it is, and they need to be there. But since those particular organisms that are designed to be in yogurt like to be there, there's other ones that also like to be there, and we want to keep them out. So it's the things that are most susceptible or designed to have microbial life in them by intent, and it's also those things that are designed to have the most at-risk end users. So in what I mean by that is, in particular, the very young babies, baby food, we typically tend to hold a higher importance on protecting the products that are consumed by young children for good reason. They have weaker immune systems, so they're more susceptible. A lot of us people on this call are probably, in general, pretty healthy and can withstand a certain amount of exposure to these organisms. But people that are very young, very old, and in any other way have a weakened immune system are much, much more susceptible. So that's why we target, with this technology, the benefits that it provides those industries in particular. And then I had a question of how often does integrity testing need to happen, and where can those integrity testers be found? So this isn't necessarily something that's black and white. It's really more of a function, especially in a process that becomes validated, how often sterilization happens to prove that it's effective. So one of the more common things in food and beverage, for example, is to do it either after production runs to ensure that everything that happened during that cycle is safe and good, perhaps daily or perhaps weekly. It's really something that ends up being specified and chosen by the user of the filter themselves. And I've seen it quite varying all the way from every production cycle, which is probably a best practice, and maybe not entirely necessary, but all the way to people that are using a sterile filter and not sterilizing at all. And that just really doesn't make any sense. If you're using a sterilizing grade filter, it really needs to be sterilized periodically, because like I said, we need to ensure that we're not exposing the media in that filter to any challenges above what the filter is qualified to remove. So unless you know that particular filter has not had a chance to be exposed to over, like I said, 10 million cells per square inch, it's basically, call it unknown what happens beyond those concentrations. So you need to sterilize periodically to make sure that those challenge concentrations are staying at or below the level for which the element's been qualified to perform at. In the test equipment itself, it's pretty widely available on the market. There's not a lot of producers of automated equipment, but the tests are typically something that can be done fairly easily manually as well. So of course, automation is beneficial for several reasons. Most importantly, in the way of removing possibility of error and variables that are caused by people doing the tests. But the equipment itself is typically either designed to do bubble point or water intrusion tests on liquid membranes, and there's also a certain variety of aerosolized droplet testers that test depth filters that are used in sterile gas applications. So that test used to be called a DOP test. It basically produces a fog of oil droplets or aerosolized oil droplets that are on average in that 0.2 to 0.3 micron size. And the machine is quite complex, but it will basically produce a certain concentration of those aerosolized droplets, pass it through a filter, measure what got through it, and calculate an efficiency value based on those concentrations.
Great. Coulter, I have another question. What is a reasonable number of steam cycles a filter withstands in a process environment?
So this is a really important one. This is, like I said, what really determines oftentimes the lifetime of one of these elements. So you always want to get as many sterilization cycles as possible. And since every single cycle isn't perfectly reproducible, there's always an opportunity for a sterile filter to be compromised, even if it's within the quantity specified by the manufacturer. These claims that manufacturers make really aren't, call it binding. They're not, for example, I guarantee you that this will last 100 sterilization cycles. It's more of a claim that means in testing by the manufacturer, on average, these things will last this long with a fairly large safety factor built in. So it's likely to last that long, but it's not guaranteed. And a good roundabout number for a lot of manufacturers is 50 sterilization cycles. That's one of the goals here that we wanted with this life tech, and it's in the name of the product itself, is we wanted to extend the life and how long people can use these. So we're advertising 100 sterilization cycles for any of our sterilizing elements under that name. And like I said, we've tested them extensively in sterilization, and they will be extremely likely to hold up to that. But of course, that really is somewhat dependent on having a proper system, the proper temperature, the proper system design, making sure no slugs of liquid in the steam system can impact the filter. That'll create, a real high, call it water hammer type of pressure slam that could damage the filter. There should be a steam filter to ensure that the steam that's being used to sterilize is clean and doesn't have any dirt, particles, rust, or shards of things that could impact and cut that media. And it's the most vulnerable time in life for a filter, and that's one of the most important things to have proper design on, and preferably automation if possible.
Great, thank you, Coulter. Looks like we don't have further questions. I do want to remind everybody, Coulter's been gracious enough to put his contact information on that slide, so feel free if you'd like to touch base with him after the webinar with any questions for him. And if you have any FPSA-related questions for me, please contact me at dalonzo@fpsa.org. Thank you, Coulter and the Donaldson Company, for sharing your expertise with us. Thank you to all of our attendees for taking the time out today to listen to this very important webinar. So thanks, everyone. Appreciate your time. Thank you, Coulter.
Thanks, everyone. Have a good day.
Too.